Okay, so we talked about the qualitative basis for Bronsted-Lowry acidity, and we went back to Gen Chem and we looked at equilibrium constants and what those things mean. We revisited the P function, what is pKa, what is pH, right? Remember that? So we did all that stuff in Chem 1, and we did it again just now with considering the quantitative aspect or basis for Bronsted-Lowry acidity. But now we're going to talk about the qualitative. So let's look here. We're going to talk about the qualitative basis for Bronsted-Lowry acidity. And this is actually the one that's going to give you the great power. So we're going to take some extra time with this video, and we're going to take some time. So I'll have you a piece of paper and some notes and ready to write this stuff down. What we're going to do is we're going to talk about how we can look at a compound, just look at it, and qualitatively assess what we think the pKa is going to be, and thereby which way equilibrium is going to lie, how good of an attacker something's going to be, how vulnerable something's going to be to attack, and so on. Ad nauseum, right? Or ad infinitum, I should say. So let's look at it now together. So the more effectively a conjugate base can stabilize its negative charge, the stronger the acid. This seems wordy. I want to stop, put a star next to it, and have you read it again. The more effectively a conjugate base can stabilize its negative charge, that is the lone pair, the stronger the acid, period. Okay? Now, there are four main factors that affect the stability of a negative charge, and we can memorize those. And we're going to use an acrostic or an acronym called ARIO, okay? The atom that carries the charge, resonance, induction, and the type of orbital on which the charge resides, okay? Atom, resonance, induction, and the orbital on which it resides. Okay, and all four of those things we can tell just simply by looking at the structure. So let's first of all look at the atom. So the type of atom that carries the charge affects very much the acidity. So look at these two molecules, butane and propanol. They are about the same size. 1, 2, 3, 4. 1, 2, 3, 4. Propanol weighs just a little bit more, and oxygen and carbon are pretty close. There's a carbon right there. Why would I do O? There's a carbon right here, right? And there's an oxygen here. They're about the same size. They're almost identical in weight. And so we look at those and we say, well, they probably should be pretty similar in their acidity, right? So the only difference is the carbon, or the atom on which the ionizable hydrogen resides. Okay, so which of these is more stable? Well, in a previous conversation, we said that the pKa of this guy was about 18, and the pKa of this guy was about 50. Wow, this would be a much stronger acid. So consequently, this is a much stronger base. This is a better acid, right? So we memorize that. I've always got these numbers in the back of my mind, right? They're a huge help to me, a huge fence around disasters, holding me off, okay? So in this pK, but the reason is simply because of that atom. So you can see that the atom has a dramatic effect on how acidic a proton is going to be. That's the first one, A, for the atom, okay? Now, let's, I just walked through this. So we know that there's two factors. The larger the atom, I didn't say what this was. I didn't say why. The larger the atom, the more stable, and the more electronegative the atom, the more stable, okay? So carbon, oxygen's a lot more electronegative. Remember the three electronegative elements? N, O, and F, right? So when you see one of these, you know you've got an electronegative element, and they're about the same size. Carbon and oxygen are pretty close in size, okay? So, but the more electronegative means it's very much more. And again, I already went back and talked about how I've got these numbers memorized, right? That the pKa of butane is about 50, and the pKa of an alcohol is about 18. All right, and that's the reason why. It's because of electronegativity. Okay? So, whoops, lost my place. Okay, so This is what we did. I got out of order here. This, I said the pKa. Remember, the pKa of this was about 18. The pKa of this was about 50, and so therefore, this is much more stable because it's a better acid, right? All right. So now let's look at resonance. How does resonance affect it? So we spent almost a whole chapter on resonance. Let's go back and look at this now. So you've got these two molecules, ethanol and acetic acid. And if you look at it, those look pretty similar, right? However, if you look at their conjugate bases, then you see that when ethanol, I don't know if I said that correctly in the past slide, but it's ethanol, right? So when ethanol donates its proton, it's left with a negative charge on an oxygen, which is not so bad, right? Because oxygen's electronegative, okay? It's not good, but it's not bad, okay? But this oxygen on the electron, on this negative charge on the oxygen is actually shared between two oxygens, right? Remember with resonance, we would say, oh, well, because neither of these resonance structures are the real thing, right? They both show how it works, right? The real thing looks like this. So the negative charge is shared over both of those oxygen atoms, right? And so this, consequently, is substantially more acidic. So I mentioned here, why don't you look up those pKa values? I happen to have them right on the tip of my tongue because I've memorized them, right? This is about 5, and this is about 18. Wow, much more acidic, right? Look those up. I think you're going to find this is actually 4.75. But if you memorize things right at low res, they sit in your head better. And you'll find that this low resolution is almost always good enough, okay? So this is about 5, which is acetic acid is way more acidic than ethanol. Okay, now the next thing is induction. So in a previous quiz that we had in class, I used trifluoroacetic acid because this is what I had in mind, okay? It turns out that when you have an electronegative element on here, you're going to be pulling electrons out that way. You know what? Let me get rid of green. This is too obtuse. Let me go to blue and say that you've got some partial charge going on there, right? You've got some polarity. So this carbon is very electron poor, right? So since it's electron poor, it's going to be able to handle a negative charge better than this, where am I here? Where's my marker? Better than that carbon, right? So watch this. So essentially, electron withdrawing groups are going to pull electrons out of the system and are going to stabilize the negative charge on a conjugate base. So let's look at what happens with that. Watch this. Oh, I don't have the picture. Let me show the picture. You have acetic acid, which looks like this, which is not bad because it's resonance stabilized, right? But then you have trichloroacetic acid, right? Which has 1, 2, 3 chlorines, or chlorides, I should say, right? Pulling because of induction, pulling the negative charge that way, which makes this even better, okay? So the more electron withdrawing groups, the more stable the conjugate base. It's going to make it the better the acid, right? So if we have acetic acid, which has a pK of about 5, okay, and we put 1 chlorine on there, it takes it down almost by a factor of 100, right? Because remember the P function, right? So from 4.75 to 2.87 is almost 100 times more acidic. And then we go down, this is now over 10 times more acidic, right? And then more yet. Okay, can you see that? I've got 3 electron withdrawing groups. Boom. 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 Right? Almost looks like a fleur-de-lis. Look at that. Okay. Wow, look at that. This is 10,000 times more acidic than acetic acid. All right, and that's the reason why. Okay. Now the next thing in our acronym is O, and the O stands for the type of orbital that can affect the stability of a formal negative charge. Okay. So the closer the electrons are to the nucleus, the more stable they are. So if you have an sp3 hybridized atom and you have a hydrogen, can I draw this? Is this going to be too ugly for you guys? Can you see this? Suppose I've got like end-to-end overlap, right? So there's a sigma bond for a hydrogen, can you see that this hydrogen is going to be closer to the nucleus, right? I may have exaggerated that some on accident, right? So the sp2 is going to be closer to the nucleus. It's, the closer the electrons are. Sorry. I don't want to draw these in there. We're talking about the conjugate base, the stabilization of the conjugate base. Sorry about that. So you can see that if you've got your lone pair of electrons that are left right here, can you see that in blue? They are not going to be as stable as the lone pair of electrons, which is here, which are not going to be as stable as the lone pair of electrons, which is here. So let's look at some examples of this. We have a triple bond here. We have a vinyl hydrogen and an alkynyl hydrogen. Okay, so what? Who cares about those terms? All right, so you can see that this is sp hybridized, and this is sp2 hybridized. So we have to consider which one is going to get donated. If we strip a proton off of there, is the conjugate base going to look like this, or is it going to look like this? Well, recall that an sp is a shorter or closer to the nucleus orbital, so it's definitely going to be this guy, right? All right, so let's look at the, are we given the pKa's here? I've forgotten now if I've got these on here. Yeah, we're on here. Okay, so we learned that the orbital can affect the stability, right, which I just now said. This one's going to be more acidic. How much more acidic? Look at this. You're going to die. Look at this. Unbelievable. So if we go from here to here, that's 1,000,000 times more acidic. 10 to the 6. This is 1,000,000 times of ethylene. It's 1,000,000 times more acidic than ethane. But oh my goodness, look at that. 10 to the 19 more acidic. Acetylene is 10 to the 19 more acidic. So an sp orbital stabilizes. This is what we're talking about then. The conjugate base is going to look like this, right? Where that is an sp hybridized carbon, right? Can you remember there's a carbon there? I know. If you're not used to line bond stuff yet, it's going to be a challenge. All right, so the orbital is another factor which is going to affect acidity. And we're going to qualitatively be able to predict it by being able to tell the hybridization of particular atoms. Okay, so looking back on this now, excuse me folks, this is my wife, and I'm not going to pause the video. Hello? Hi, honey. Okay. Okay, I'm doing a video, honey, right now, so I will. Okay, love you. Bye-bye. Okay, pardon me. Now, when assessing the acidity of protons, we generally use ARIO, okay? And you've got that. It's very useful, okay? I think I've already told you, let's go back here. I've already told you that I've got this table memorized in my head, so I'm using ARIO plus a table in my head, right, of 21 pKa's. It's typically useful, but it's not 100% reliable. Let's look at some exceptions. Okay, ethanol is more acidic than propylene. Okay, ethanol, you can see, is way more acidic than propylene, right? Now, the type of atom is consistent with this fact, okay? But propylene conjugate base, propylene anion, I don't know what we call this thing, is resonance stabilized, right? This could, you might go, oh wait, this is resonance stabilized. And Dr. Kopic, you said resonance was a huge deal, and I did, and it is, okay? But in this case, its resonance is not nearly as important as the atom, all right? So it says, to the point of this slide here is to show you that that's the most important, that the atom is more important than resonance, okay? But that's not always the case, right? Sometimes it fails. For example, if we look at this, we'd say, oh, well, let's look at these conjugate bases. So I've got an electronegative element here, right? Remember? Electronegative element, N, O, or F. And so I see a negative charge on electronegative element. I go, oh, that's much better than having a negative charge on a carbon, right? So this must be more stable. That's what you're thinking. This must be more stable. But it's not. Okay, so this is an exception. And it turns out that since we went to our pKa tables and wrote these pKa's out, we know that the lower pKa always gets to act like the acid, right? So you take the lower one and you push the arrow away from it because this is the stronger acid. And so this is going to be the weaker base or the more stable base, or we'd say that equilibrium lies in that direction. All right, I think that's it. We spent a little bit extra time with this concept. Memorize this acronym ARIO. Memorize the trend, and I'm also going to encourage you to get a list of 10 or 20 pKa's and memorize those, and it can help you see these exceptions coming. All right, good luck.